Today's challenge is called Cosmic Claw. It focuses on how robots are used in space exploration. Robots are ideal for doing repetitive or dangerous tasks that require precision. Robotic arms are used in the military, medical, industrial, and even agriculture fields. Agriculture or farming provides the food and raw materials humans need to survive. Farmers use robots to cultivate crops and care for livestock. Robots will play a big role in the future of space exploration and may have to perform a variety of tasks that would be too dangerous or difficult for humans. The Mars Perseverance rover is a robot on Mars, which is too dangerous for humans. The robotic arm attached to Perseverance is 7 feet long and composed of shoulder, elbow, and wrist joints that make it as flexible like a human arm. It takes geologic samples and records microscopic images of Martian rocks. There is also a robot arm on the International Space Station.
In the next few years, the moon will be a testing ground to help us learn how to live and explore space. NASA's next mission to the moon will focus on sustainable space exploration. Exploring space to the farthest reaches of our solar system and beyond will require a lot of resources, and returning to Earth every time astronauts need more resources won't work. That is why we need to figure out ways to support the survival of humans independent of Earth's resources. Right now, the International Space Station typically has enough food and other supplies to last several months. Most of the water and oxygen are recycled on board the space station. Even sweat, urine, and water vapor from the air and are purified and reused. However, if a resupply shuttle with food gets delayed, the astronauts have no choice but to try and conserve food supplies by simply eating less. The next generation of space explorers will need to know how to harvest food, water, and oxygen while traveling in deep space. Robotics and agriculture will be essential for sustainable space exploration. Your challenge today will be to prototype a robotic arm that could be part of the future of agriculture in space.
Let's see how one of the robotic arms used in space exploration today looks like, and how what we learned in space is also used here on Earth.
Space represents a fairly harsh environment. Any piece of equipment that's exposed to it over a long period of time would require maintenance.
So every time we have to do a maintenance on the outside of the space station, that means a crew member has to suit up and go outside. That introduces that crew member to risk and puts that person in harm's way. The other issue is that now they're spending the time doing the maintenance work, and they're not doing the science, which is really what their purpose is. So with the maintenance challenges that we were going to have with the International Space Station, what we found ourselves was Canada being in the position to provide a solution to that problem, and Dexter was going to be that solution.
Dexter is a 2-armed robotic manipulator system capable of performing fine motion tasks to replace what an astronaut would need to do on the exterior part of the space station.
Dexter is essentially a handyman. It operates on the outside of the International Space Station. It allows us to do maintenance operations. One of the advantages with Dexter is that we're able to control it from the ground.
And so the ground crew could actually operate these robotic systems and free the astronaut up from that task as well.
So now that Dexter's online on the space station and operating on a regular basis, what we've got a crew who's spending more time doing science. And this is important because this was really the whole idea of building the International Space Station, was to be able to do science in low Earth orbit.
Unfortunately, only about 40% of women should be getting annual MRI as part of their screening undergo MR screening. Part of the reason why women were not undertaking MRI screening was because of lack of access to the best radiologists locally.
Some women have to drive very long distance, like 7 or 8 hours of car in snowstorm during the winter, sometimes risking their lives just to get their MR-guided breast biopsies.
When we started to do the research with Canadian Space Agency and NASA on the whole remote telesurgery, we started to get involved with MDA. MDA is a Canadian company which has been involved in manufacture of all the robotic systems which is currently used on the space station.
So we developed a system called IGAR, which stands for Image Guided Automated Robot.
IGAR is a teleoperated robot that performs breast biopsies under MRI guidance.
One of the capabilities of IGAR is to be controlled by radiologists from any distance. And that allows basically radiologists to supervise MR breast biopsy on a patient who may be hundreds of kilometers or thousands of kilometers away from them. It means that the patient can undergo their breast biopsy in their own local hospital without having the need to travel to another city or another hospital to get access to the expertise.
And the results are very, very encouraging. So we've demonstrated that the IGAR is safe, extremely accurate as a human.
And this will allow us to hopefully increase the number of people undergoing screening close to 100% where it should be. So IGAR is built on many of the know-how which was developed for the space program, as well as the software which is also used to control the robotics on the space station.
We can actually see some of these technologies we worked with for a long time becoming available. We have a lot of insight on how to apply them, not just in medicine, but in a number of other fields, which is what we're doing. So without the space station, would any of that have happened? No, not really. Not in that way, anyway.
We're going to be building a prototype arm and using the engineering design process for agriculture and space. What do you think this arm will do? For this challenge day, we'll be using the engineering design process. The engineering design process shows us the steps we go through when building something. This process is especially useful when working with robots. Our first step is to identify the challenge. Today we will provide you with the challenge, but this may not always be the case. After you know the challenge, we go to step 2, brainstorm. In step 2, we will brainstorm ways to solve the challenge. After step 2, we move on to step 3, build. In step 3, we take the idea we created in step 2 and physically build the structure. Next is step 4, experiment. In step 4, we test out the prototype we built in the previous step. Our machine may not work, and that's okay. In step 5, we improve our design. We reflect on what worked and what didn't, and look at the problems in our design. Now that we know what went wrong, we can go back to step 2 and brainstorm how to solve the problems from the first prototype. We will follow this cycle until we are happy with our design. One thing to remember is that our first prototype will never be perfect, and that is why we have the engineering design process. We can continue this process until we are happy with the product. Now we will have to use the hydraulics to power the Cosmic Claw. Hydraulics use liquid, we'll use water, through pipes and tubes to power mechanical movement. The first step will be to build the hydraulics. Then we will build the first prototype. When everyone has a working prototype, I will show you the harvest challenge and you'll see what your Cosmic Claw has to do.
Have your supplies ready and turn to the instructions on page 15 of the Cosmic Claw Youth Guide. For now, you will need the 2 cylinders, the tubing, the 2 small screws, some water, and a screwdriver. First, fill both cylinders with water. Place the tip of each cylinder in the water and pull the piston away from the tip to fill the cylinder with water. Fill the tubing with water by attaching a full cylinder to one end and pushing the piston. Repeat the process as necessary to fill the tubing completely with water. Next, attach the second cylinder to the opposite end of the tubing. Remove all bubbles from the cylinders and tubing. Tip the cylinders so any bubbles rise to the base of the tube. push the air out and refill. Last, use a screwdriver to put a small cylinder screw in the end of each cylinder to secure the tubing. Well done! You've assembled the hydraulics for your Cosmic Claw. Test them out, then we'll assemble the arm.
Before we move on to the next step, check with your facilitator to see if you should design and build the prototype on your own or continue following the instructions. The illustrations for the next part are on page 16 in your workbook. For this step, you will need your hydraulics, the rest of the supplies in your kit, a screwdriver, and a wire cutter. First, we're going to use the wire cutters to cut 2 long black strips in half. Now, take one of the half-sized and cut it in. Now you should have 2 pieces that are 3 inches long and 3 that are 10 inches long. Screw the 3-inch strips together at each end. Use 2 screws to attach the 3-inch strips approximately 3 holes away from the joints. These shorter pieces should go in the middle of the U shape, but aren't attached in the middle yet. Use a screw to attach the red part of your cylinder to the end of each of the 3-inch strips where they meet in the center. The clear rectangle part of the cylinder has a pin. Pop that into one of the holes along the 6-inch piece. Now all your pieces should be connected together. Now that everything is connected, move the red part of the cylinder not attached to the Cosmic Claw. What happens to the end of your claw? Test the movement of it. If you have trouble with your cylinder not staying connected to the 6-inch strip, add a wire tie to hold it in place. Our human bodies are well adapted for life on Earth. Spending even a few days in the weightless environment of space can cause severe muscle loss and even negative effects. Therefore, we are studying how to keep astronauts and future space explorers fit and healthy during long periods of time. Scientists are experimenting with training routines and diets that will provide the nutrients needed and exercise astronauts need. Future space travel will also rely heavily on harvesting and processing raw materials to sustain human life in space travel. For this reason, the fields of chemistry, mineralogy, metallurgy, mining, and more will be used to capitalize the resources that are available independent of Earth. In addition, policymakers, leaders, and diplomats will put their skills to the test to create the legal framework surrounding space exploration and property rights for interstellar corporation. Consider these careers related to space exploration: astronaut, chemist, dietitian, electrician, engineer, geoscientist, medical professional, metallurgist, nutritionist, physiologist, technician.
Now that you have your prototype built, I will explain the challenge. You will have 10 minutes to use the engineering design process to adapt your prototype for the mission. Your facilitator has some additional supplies you will use to make your adaptations. Here is your challenge. Your crops are ready for harvest, but the planet you are on gets limited sunlight. Your team will need to work fast to pick up and dump as many crops into a container as possible. These pom-poms will represent the crops your team is harvesting. You need to get them from the tabletop to the harvest bin here. Your team will only have 1 minute to harvest as many crops as you can. What can you design to put on the end of your prototype to help you for grasp, scoop, or rake the crops quickly into the bin? Use the engineering design process for this challenge. Show each other what your cosmic claws can do. Each team will take a turn to demonstrate their prototype and share what they think works best in their design. Your prototype may not work perfectly yet, but what is working best?
We have a second challenge you can try if you have time. In this challenge, your team needs to use the engineering design process to adapt the cosmic claw to stow the food that are growing so that they can be stored. There isn't a lot of space in your vessel, so you need to store all the crops in a space that is half the size of your harvest bin. For this challenge, you need to divide the harvest bin in half, then pick up and neatly stack the crops for storage. How many crops can you stack in a designated space? You have 10 minutes to adapt your cosmic claw and your storage space to keep the crops safe in a long-term storage. Check with your facilitator to see what supplies you can use for this challenge. Give teams 10 minutes to alter the design of their cosmic claw and storage bin as needed to complete this new challenge. Teams should test each new design to determine which design works best. Let's see how good your cosmic claw are at being precise. Each team will take a turn to demonstrate their prototype. Just like in the first challenge, you will share what works best in your design and what would you do to improve your next design.
Do you remember how we started off today? I told you that we were going to learn about how robots are used in space exploration. We talked about how space explorers will need to know how to grow and harvest food while traveling in deep space. Robotics and agriculture will be essential for sustainable space exploration. How did it go for your team, building, testing, and improving your prototype for different jobs in space? What would you do differently next time? We are just starting to learn how to grow food in space. There are a lot of ways technology is used in space. Today, you learned about robotics and hydraulics and used that to build a hydraulic arm that can be used in many ways, similar to the Canadarm on the International Space Station. What would you want to grow if you were a space explorer?
But that's not all you did. You were also developing your teamwork skills, learning to collaborate and communicate with your team. You were problem solving and engineering solutions to the problems you faced. These are all important skills that you learn in school and in your after-school program. When do you have to work in a team to solve problems outside of your after-school program? Today, you are learning about how technology is used in space, and you are building skills that will help you be successful in school and in the real world. Thank you for joining us today.